So in our previous video, we talked about the ideal gas law, which provides a connection between pressure, volume, and temperature of a gas. Changing any one of those variables causes one or both of the others to change. One of the things that we can do, though, is if we can isolate one of those variables and keep it constant, we can formulate three different gas laws that we're going to look at, and we're going to then look at different gas processes using those three laws. The three laws we're going to look at are called Boyle's Law, Charles' Law, and Gay-Lussac's Law. Those three gas laws describe the behavior of a gas system that undergoes a change. We're going to take a look at those and begin to look at what are called PV diagrams, or pressure volume diagrams. So here we go. So suppose you get up one cold morning and you go out to your car and you measure the pressure in the tires of your car. You then get in the car and you drive on the highway for about 30 minutes. This warms up the tires, and then you test the pressure again after stopping the car, of course. What you'll find is that the pressure in the tires has changed. The question is, how much? What does the pressure in the tires change? In Boyle's law, the pressure and volume change while the temperature stays constant. With Charles' law, the volume and temperature change while the pressure stays constant. And Gay-Lussac's law, pressure and temperature change while the volume stays constant. These three gas laws can be put together into what we call the combined gas law. To use the combined gas law, we have to establish that the quantity of gas is fixed. We're not going to add any gas or remove any gas. All the processes then that we're going to consider, these gas processes we're going to look at, will involve a fixed amount of gas. Second, that there's a well-defined initial state. See, there's an initial pressure, there's an initial volume, there's an initial temperature. And then there's a well-defined final state, a final pressure, a final volume, and a final temperature. And each of these variables here, we can be represented in a diagram that we call a PV diagram. Let's take a look at one. So a PV diagram stands for pressure over volume. And these diagrams allow us to find the pressure, the volume, and the temperature of a gas at any point. What I mean is, on a PV diagram, each point on the graph represents a single unique state of that gas. Now, even though each point represents only the pressure and volume at that point, because we know the ideal gas law, we could figure out the temperature. So each point on a PV diagram actually represents a triplet of values: the pressure, the volume, and the temperature, specifying the state of that gas. For example, this figure here is a PV diagram showing three states of a system consisting of 1 mole of a gas. The values of pressure and volume can be read from the axes. Then the temperature at each point can be calculated from the ideal gas law. Let's take a look at point 1 here. At point 1, the pressure is about 7.5 kilopascals. So we can put 7,500 pascals in here, while the volume is sitting about 1 cubic meter. We've established here that it's 1 mole of gas, and so then we put in our gas constant. We get a temperature of 903 Kelvin, which is what is shown here. And we could do the same thing at point 2 and at point 3, and we'd get about the same temperature shown here. Now, an ideal gas process is a process that changes one or more of the three variables of a gas. For example, we can heat the gas or we can compress the gas. And these are ideal gas processes. Ideal gas processes can be represented as a trajectory on a PV diagram. So in this figure here, this is part B of the previous figure, so we have the same 3 points, but we've got here is showing one possible process by which the gas of part A is changed from state 1 to state 3. So we're going to look at 4 thermodynamic processes: isobaric, isochoric, isothermal, and adiabatic. We're going to look at each of those processes individually in the next video, but each of them follows the same basic format. For each of them, we start out with a system of gas, okay? And that system of gas is going to have an initial internal energy. Then we're going to add heat energy to the system or take that heat energy away from that system. So in each of these processes, energy is added or removed. Okay, so heat is involved in each one of the processes. Work may or may not be involved in each of the processes. Okay, so in some of these processes down here, work is done. That's mechanical work, like compressing a gas is mechanical work. So in some of these, work is done. In others, work is not done. Regardless, we're going to end up with some final energy state of that gas. So we're going to look at each of those processes in the next video.